in the last few lectures we developed the theory of radiation or antennas. In this session we solve some problems based on the theory which we have developed for radiation and antennas. So let us take a problem here. There is a Z oriented Hertz dipole of length 10 centimeter excited with a sinusoidal current of amplitude 20 amperes and frequency 10 megahertz. Find the instantaneous electric field at a distance of 1 meter along the x axis at 1 microsecond. Also find the orientation of the electric field. So this is a simple problem based on the theory which we have developed for the Hertz dipole. So the problem which is given here is we have a Hertz dipole. So let us write down the coordinate system. So let us say this is the direction, this is x, this is z, then the y will be oriented this way, and we have a Hertz dipole here of length 10 centimeter, that is 0.1 meters, and the peak current is 20 amperes. So we have here, this is I into dl, and then this IDL for this problem will be 20 into 0.1, that is equal to 2 amperes meter. So that is the current moment for this dipole which is given here, and then we require now for calculation of the electric field the quantity beta. So first we have to calculate the angular frequency omega, then the radiation is going in the free space, so the velocity is equal to velocity of light. So we can get from there first the omega equal to 2 pi into 10 megahertz, so it is 10 to the power 6, so that is equal to 2 pi into 10 to the power 7 radians per second, and then the phase constant beta, which is omega pi c, is equal to 2 pi into 10 to the power 7 divided by 3 into 10 to the power 8. So that is equal to pi upon 15 radians per meter, and the distance r is given as 1 meter from the antenna at a time which is 1 microsecond. So here we assume that at t equal to 0 the current is maximum in this Hertz dipole and it will be flowing upwards. So we can take the current variation as cosine of omega t, and then we can calculate what will be the field after a time of 1 microsecond at a distance of 1 meter from the Hertz dipole. So once you get beta, then we can get beta r, that is equal to pi upon 15 into r, which is 1 meter. So that will be equal to pi upon 15 radians. And we can get this quantity beta t omega t, that is equal to 2 pi into 10 to the power 7 into 1 microsecond, which is 10 to the power minus 6. So that is equal to 20 pi radians. So now we got all the basic quantities required for calculation of the electric field, and in general we have the electric field which has 3 components, r, theta and phi, and in this case we are looking for in the direction which is x axis. So we want to find out the field in this direction. So for this the theta, which is measured from the z axis, that angle theta is equal to pi by 2. R direction, which is going outwards in this direction, so that is same as r direction also. So essentially we have the electric field Ex, which is equal to Er. The theta direction is in the going downward like that. So in this case the theta component will be opposite to the z axis. So, we have from here the theta component E theta equal to minus E z. That is the way the E theta component will be oriented. So, now we can calculate using the expression which we have derived for the total field from the Hertz dipole. We can get E r, that is same as E x in this case, which is equal to I 0. The I 0 is the peak current, which is same as this. So, we got I 0 dl cos of theta divided by 4 pi omega epsilon into beta upon r square minus j upon r cube. And in this case, since theta for this point, which is 1 meter away along the x axis, theta equal to pi by 2. So, this cos theta will be equal to 0. So, in this case E r equal to E x, that will be equal to 0. The theta component for the electric field E theta, which is same as minus E z, that is equal to I 0 into dl into sin theta upon 4 pi epsilon, and we want to find out now the electric field at some instant of time. So, we take the real part of e to the power j omega t minus j beta r multiplied by j beta square upon omega r plus beta upon omega r square minus j upon omega r cube. These are the expressions which you already derived when we were analyzing the Hertz dipole. So, now we can substitute different values here. The I 0 dl we have got is 2, the beta r is pi upon 15, the omega t is 20 pi. So, if you substitute all these quantities in this and epsilon equal to epsilon 0 for the free space, you get E theta will be equal to 0.1932 volts per meter. And as we know, for the Hertz dipole, the phi component of the electric field is 0. So, we get E phi equal to 0. So, in this case, if you move along the x axis, then the r component is 0, the theta component, which is same as the minus z component, and the phi component also is 0, which will be perpendicular to the plane of the paper. So, by using the expression which we have derived, now we can find out the total field at a distance and at some instant of time from the Hertz dipole. Let us take next problem. A vertical Hertz dipole radiates 1 kilowatt of power. Find the electric field and the Poynting vector at a distance of 10 kilometer from the dipole in the horizontal plane passing through the dipole. What is the direction of the electric field at the observation point? So, in this case, the total power which is radiated by the dipole is given and we have to find out the electric field at a distance of 10 kilometer. So, the problem is we have the Hertz dipole here, the horizontal plane which is passing through this, which will be this. So, at a distance of 10 kilometer in this direction, you have to find out the electric field. As we know, again the electric field here, if I take the standard coordinate system, this is the z axis, and if I take a plane which is perpendicular to the dipole, then we have theta component which will be oriented like this. So, the electric field is vertical at this location. And now, by using the relation which we have derived, we can find out what is the electric field at this location. So, first what we do, we have already derived the expression for the total power radiated by the Hertz dipole. So, we know that the power radiated W is 1 kilowatt, that is what is given, that is equal to 40 pi square I naught square dl upon lambda whole square. Now, from here we can calculate this quantity I0 dl upon lambda. So, we can invert this to get I0 dl upon lambda, that is equal to 1 kilowatt, which is 10 to the power 3 watts, divided by 40 pi square root. So, that is equal to 5 upon pi. Now, at this location, the theta, this is z axis. So, theta in this case is again 90 degrees, is pi by 2. So, we can get the electric field, magnitude of the electric field, that will be equal to I0 dl beta square upon 4 pi epsilon omega into r. The omega upon beta we can separate out. So, this we can write as I0 dl upon 4 pi epsilon. We can write here beta upon omega into beta, and omega upon beta is nothing but 1 upon velocity of light, and this is 2 pi upon lambda. So, we can get this equal to I0 dl upon 4 pi epsilon 1 upon velocity of light multiplied by 2 pi by lambda for beta. So, substituting now for this, we get mod of electric field, that will be equal to 1 upon 2 pi r into c into I0 dl upon lambda. Now, we have already derived the value for I0 dl upon lambda, which is 5 upon pi. So, if I substitute that, I get the mod of electric field, that is equal to 30 millivolts per meter. The next thing which you have to find out in this problem is the horizontal plane passing through this. We want to know the electric field and the Poynting vector at a distance of 10 kilometer. So, we found the electric field. Now, we have to find out what is the Poynting vector at that location. So, we know that Poynting vector P, the magnitude of that is equal to mod E square upon eta. So, that is equal to 30 into 10 to the power minus 3 per millivolts square upon eta, which is 120 pi. So, if I simplify this, I get the power density, which is 3 into 10 to the power minus 4 upon 40 pi watts per meter square. So, this is again a very simple problem where the total power radiated by the Hertz dipole is given, and then we are asked to find out what is the electric field and the Poynting vector at a distance of 10 kilometer from the Hertz dipole. Let us now take some problem based on the dipole which is having a finite length. As we know, the Hertz dipole is infinitesimally small, its size is much smaller than lambda, whereas in practice we require dipoles which have substantial length. So, in this case the problem is a 1.2 lambda long dipole has 1 ampere peak input current. Find the maximum peak current seen on the dipole. If the dipole is oriented along the z axis, find the radiation, electric field and the magnetic field at a distance of 100 meter along theta equal to 60 degrees. So, first of all we have to get the expression for the field for the Hertz, this dipole which is having a length of 1.2 lambda, and then from there we can essentially calculate, substituting the parameter, the field at an angle theta equal to 60 degrees at a distance of 100 meters. Now, as we know, the dipole has a length of 1.2 lambda. So, h, which is half this length for the dipole, this we call as h. So, h is equal to total length of the dipole, which is 1.2 lambda divided by 2. So, that is equal to 0.6 lambda. So, this length is little more than lambda by 2. So, we get a current distribution which will look like that. And that is the current which is the maximum current which we are going to see, Im, and this will be the input current which will correspond to this value. So, now as we know, the current I, input current at this location, so that is In, that is equal to Im sine of beta h, and this current is given as 1 ampere. The input current, peak current is 1 ampere. So, this quantity is 1 ampere. So, that is equal to Im sine of beta, which is 2 pi by lambda into 0.6 lambda. So, this quantity is 1.2 pi. So, you get Im is equal to sine of 1.2 pi, and the I maximum will be equal to 1 upon this quantity. So, this will be 1 upon sine of 1.2 pi, which is equal to 1.7 amperes. Once we get this quantity Im, then we know that this dipole for the radiation field has only theta component, E theta, and that is equal to 60 Im upon r, where r is the distance measured from the center of the dipole, cosine of beta h cos theta minus cos of beta h upon sine of theta. So, now the distance is given as 100 meters, the theta is 60 degrees. So, we can substitute now for these parameters here. So, here we are given that r is equal to 100 meters, theta is equal to 60 degrees, that is equal to pi by 3. So, the theta component of the electric field will be equal to 60 Im, which is 1.7 amperes, divided by 100 meters into cos of 1.2 pi, that is beta h, multiplied by cos theta, which is 1 by 2. So, this gives cos theta equal to 1 upon 2. So, we can get here, which is beta h cos theta, that will be 0.6 pi minus cos of 1.2 pi upon sine of pi by 6, pi by 3, that is equal to root 3 by 2. So, simplifying this, we can get the value for the electric field, that is approximately equal to 0.09 volts per meter. Once I know the electric field, then I can find out the magnetic field. Since I know the relation between the electric and magnetic field, that is H phi for the radiation field is equal to E theta upon the intrinsic impedance of the medium, which is 120 pi. So, this will be H phi will be equal to 0.09 upon 120 pi, that is equal to 0.24 milliamperes per meter. So, in this case we were given the finite length of the dipole, which is 1.2 lambda, then the input current is given, and then we are supposed to find out what is the maximum current which we will see on the dipole, and also the electric field at an angle theta equal to 60 degrees. So, this is 100 meters and this angle is 60 degrees. At this point we were supposed to find the electric and magnetic field. So, that is what we did. We use the expression for E theta, substitute these values, then you get the value for E theta. Once you get E theta, then we can find out H phi, which is E theta upon the intrinsic impedance of the medium. Let us now take a problem which is general problem for the antenna, and that is the field radiation pattern of an antenna is given by f theta, which is equal to sine of tan cos theta divided by sine of 2 cos theta, where theta varies from 0 to pi. Find the directions of the null, direction of the maximum radiation, and also the half power beam width of the antenna. So, without specifying what kind of antenna this is, essentially the radiation pattern directly has been given, and we have to find out now the directions of the nulls, direction of maximum radiation, and the half power beam width. Now, as we know, the nulls correspond to f theta equal to 0. So, if I take this function and equate that to 0, we will get the directions thetas for which the field will go to 0. So, the nulls of this antenna would correspond to f theta is equal to 0, that is sine of tan cos of theta, that should be equal to 0. Provided the denominator is not equal to 0. So, for those angles for which this quantity goes to 0, that will not represent a null, but otherwise for all those values of theta for which the numerator goes to 0, we will get a null for the radiation pattern. So, provided sine of 2 cos theta is not equal to 0. So, from here essentially we get tan cos of theta, that will be equal to plus minus m pi, where m is an integer. So, m is equal to 1, 2, 3 and so on. So, we get cos theta null, that is equal to plus minus m pi upon 10. Now, since cos of this angle the magnitude of that should be always less than or equal to unity. Essentially that means this quantity m pi upon 10 should be less than or equal to 1. So we have a finite number of angles because we have this quantity should be less than or equal to 1. So we get nulls only for those values of m for which m pi upon 10 is less than 1. So we get nulls only for values of m which satisfy m pi upon 10 less than or equal to 1. That means this quantity here m can go only 1, 2, 3. If m becomes 4, then this quantity is greater than 1. So essentially the possible values of m we get m equal to 1, 2 and 3. So substituting now this value for m equal to 1, 2, 3, we get the nulls that would correspond to theta nulls, that will be cos inverse of plus minus pi upon 10, cos inverse 2 pi upon 10 and cos inverse 3 pi upon 10. And as is given, theta lies in the range 0 to pi. So from here we can find out the corresponding values of theta. So we get theta nulls, that is equal to 19.53 degrees, 51.07 degree, 71.69 degree, 108.31 degree, 128.93 degrees and 160.47 degrees. So the radiation pattern has 6 nulls in the range theta equal to 0 to pi. The angle corresponding to theta equal to pi by 2, the denominator of f theta also goes to 0, making theta equal to pi by 2 as the direction of maximum radiation. So if I look at here, if I put theta equal to pi by 2, this quantity is 0, theta equal to pi by 2, this quantity is 0. So we may get a null corresponding to theta equal to pi by 2 here, but that does not represent a null because for that the denominator also goes to 0, and then that direction essentially is the direction of maximum radiation. So we get direction of maximum radiation that is theta max is equal to pi by 2. Now to find out the half power beam width of the antenna, essentially we have to take this field expression, find out what is the magnitude, maximum magnitude which you can get for this field, then you find out the angle for which the field will reduce to 1 over root 2 of its maximum value, and the angular difference between these two angles essentially will give the half power beam width. So in this case we have a beam. So if I measure, let us say theta going from 0 to pi, then we have a beam which looks like that. This is theta equal to 0, this is theta equal to pi, and we have a direction of maximum radiation, that is theta equal to pi by 2. So we have to find out now the half power beam width. That means we have to find out these two angles. This is angle theta 1 and this angle theta 2. at which the field reduces to 1 over root 2 of this maximum value. So, first we have to find out the maximum value of this expression, and since that theta equal to pi by 2, this is 0 by 0, essentially you have to calculate this by taking a limit when theta tends to pi by 2. So, for this we can expand this. So, for maximum value of the function f theta maximum, that would be the limit when theta tends to pi by 2 of this expression, which is sine of 10 cos theta divided by sine of 2 cos theta. Expanding this sine function, we get this is limit theta tends to pi by 2 10 cos theta minus 10 cos theta cube upon factorial 3 plus and so on. This is the expansion of the sine function. So, here you get 2 cos theta minus 2 cos theta whole cube upon factorial 3 plus and so on. Now, taking this cos theta common from numerator and denominator, and then when theta tends to 0, theta tends to pi by 2, cos theta will tend to 0. So, all these terms will go to 0 except this term, which will give the value equal to phi. So, the maximum value of the radiation pattern is phi. So, for half power points, mod of f theta should be equal to 5 upon root 2. So, in this you have the maximum value, this is equal to 5 in the radiation pattern, and this point now is 5 upon root 2, this is 5 upon root 2. Now, this thing cannot be solved analytically. This expression should be now equated to 1 upon root 2, 5 upon root 2, and this thing has to be solved numerically. So, we have to get the values for these two angles theta 1 and theta 2 essentially by solving that expression numerically. So, we solve numerically the expression sine of 10 cos theta upon sine of 2 cos theta, that is equal to 5 upon root 2. And there we get the values, two angles theta 1, that is equal to 82.08 degrees, and theta 2 is equal to 97.93 degrees. So, the half power beam width for this antenna is equal to theta 2 minus theta 1, that is approximately equal to 16 degrees. So, depending upon the radiation pattern, one can solve the half power beam width analytically, or if the expression is not analytically solvable, then essentially you find out the angles at which the field reduces to root 2 of its maximum value by using numerical techniques, and then one can find out the half power beam width of this antenna. Let us take one more problem. which is now related to the directivity of the antenna. There is an antenna which is fed with 100 watt of power. The efficiency of the antenna is 80%. If the radiation pattern of the antenna is given as p theta equal to sine square theta sine square phi, where theta varies from 0 to pi and phi varies from 0 to pi and 0 elsewhere. Find the radiation intensity in the direction of maximum radiation. Also find the power density at a distance of 10 km in the direction of the maximum radiation. So, this problem, there are various points to be noted. Firstly, the antenna is not radiating full power. There is the efficiency which is 80%. That means whatever power is input to the antenna, only 80% of that power is radiated in the space. Secondly, since we have a radiation pattern which is given by this, the power is not uniformly distributed in all directions. So, the radiation intensity in the direction of maximum is increased compared to the isotropic antenna, and that increase essentially is related to the directivity of the antenna. So, we have to calculate the directivity of the antenna. We can calculate the radiation intensity for an isotropic antenna once we know the power radiated by the antenna, and then from there we can calculate the electric field or the power density at a given distance. So first we note the power radiated, W, that is equal to power input multiplied by the antenna efficiency So, it is given the input power to the antenna is 100 watts and the efficiency of the antenna is 80%, that is 0.8. So, the total radiated power is 80 watts. Now, if this power is given to the isotropic antenna, then it will create uniform distribution of the power, and the radiation intensity will be, if I distribute this power uniformly over 4 pi solid angle, then the power per unit solid angle is the radiation intensity. So, in this case essentially we get the radiation intensity for an isotropic antenna and that radiation intensity we call as the average radiation intensity. So, that U average is equal to 80 divided by 4 pi solid angle 4 pi watts per steradian. Now, we know the maximum radiation intensity which we can get from the antenna is the average radiation intensity multiplied by the directivity of the antenna. So, U maximum, that is equal to U average multiplied by the directivity of the antenna. So, now to find out the maximum radiation intensity, first we have to find out the directivity of the antenna from the radiation pattern which is given here. And note here the radiation pattern which is given here is p theta, that is the radiation pattern straight away for the power. So, now we can go and use this radiation pattern to find the directivity. So, the directivity of an antenna is equal to 4 pi upon the power pattern p theta integrated over 4 pi solid angle So, this we can write down explicitly in terms of the spherical coordinates. So, this is 4 pi divided by phi, which varies, the radiation pattern is non-zero only over this range of phi, which is 0 to pi. Same is true for theta, that the radiation pattern is non-zero only over this range, which is 0 to pi. So, we have a limit here for phi, which is equal to 0 to pi. For theta also we have a limit 0 to pi, and the power radiation pattern is given by theta sine square phi. So, this is sine square theta sine square phi, and the incremental solid angle is sine theta d theta d phi. So, this will give us 4 pi divided by 0 to pi for phi. So, this is sine square phi d phi, 0 to pi sine cube theta d theta. This integral we can solve by expanding this in cosine of 2 phi, and this one we can write as 1 minus cos square theta and sin theta. So, the two integrations can be written as this is 4 pi from 0 to pi. This we can write as 1 minus cos of 2 phi upon 2 d phi. The sin square phi we can write like that, and for theta we can write here as sin square theta into sin theta, and sin square theta we can write as 1 minus cos square theta. So, this we can get 0 to pi 1 minus cos square theta sin theta d theta. Now, in this integral we can substitute for cos theta equal to t. So, sin theta d theta will become dt. So, this integral is now very simple to solve. So, you get finally a value which is 4 pi divided by pi upon 2, and that is 2 upon 3, this value. So, you get a directivity for this antenna which is 12. Once you know the directivity, then now I can calculate the U maximum, which is the average radiation intensity, which is 80 upon 4 pi steradian multiplied by directivity, which is 12. So, from here we can get 80 upon 4 pi into directivity 12. So, that gives us 240 upon pi watts per steradian. That is the maximum radiation intensity which we get. Now, the pointing vector in that direction at a distance we can calculate, because we know that the power density P is the radiation intensity divided by r square. And it is given we have to find out this power density at a distance of 10 kilometer in the direction of maximum radiation. So, since we have found out the radiation intensity in the direction of maximum radiation and r is 10 kilometer, we can substitute into this. So, this is 240 upon pi divided by 10 kilometer. So, which is 10 into 10 to the power 3 whole square. So, that would give us 0.764 microwatt per meter square. Once we know the power density, then we can find out the electric field at that point, because the power density P is mod of E square divided by eta, So, E electric field will be equal to square root of power density into eta. So, equal to square root of 0.764 microwatts per meter square. So, this is 10 to the power minus 6 for microwatts into eta, which is 120 pi. So, simplifying this, essentially we can get the expression for the value for the electric field at that distance. So, see in this problem what is given, the total input power is given, the efficiency of the antenna is given, the power radiation pattern is given, and we are asked to find out the maximum radiation intensity, the maximum power density at a distance of 10 kilometer, and also the maximum electric field. So, first we find out what is the power radiated by the antenna, then we find out the directivity of the antenna, and then using this relation we find out the maximum radiation intensity, which is average radiation intensity multiplied by directivity. And once you get maximum radiation intensity, then you can calculate the power density, which is maximum radiation intensity by r square. And once you get the power density, then we can find out the electric field, which is square root of power density multiplied by the intrinsic impedance of the medium. So, these are some representative problems essentially which we see in practice. So, if we systematically follow the analysis which you have developed for the antennas or the radiation, then the problem essentially can be split into small parts, and one can solve the complicated problems by using a systematic approach. So, once we understand the theory properly for the radiation and we can physically visualize these radiation patterns, then the solution of the antenna problems rather become extremely simple. So, these problems which we have discussed today essentially give us some feel how the radiation related problems will be used or will be solved in practice. In fact, these are the problems which we will normally encounter in designing, for example, the microwave links, or for designing the satellite communication antennas or the radar antennas and so on. So, this essentially completes our discussion related to the radiation or the antennas.